Projectile motion. The problem. A ball is on top of a 62-meter cliff and is being fired at 6 meters per second at an angle of 30 degrees above the horizontal. When the ball is fired, a 2-meter tall car is 40 meters from the base of the cliff and is moving at a constant speed towards the cliff. What velocity must the car be going to be hit by the ball? So to start off, we'll draw a quick diagram. We have the car 40 meters away from the cliff, moving towards the cliff. We have the 62-meter tall cliff, and we have the ball being fired at 6 meters per second at 30 degrees above the horizontal, and we have a rough sketch of the pattern that the ball is going to follow during its flight. Step number 1 is to break up the launch vectors. The 6 meters per second is not very useful to us by itself. We need the horizontal and vertical components to be able to do some calculations with it. So we end up with a initial velocity on the horizontal component of 5.1962 meters per second and a vertical initial velocity of 3 meters per second. So now we can make a chart. We can also fill in some other information that we know. We can start with the horizontal section. So we calculated on the slide before our initial velocity of 5.1962 meters per second, but there is no acceleration. In this problem, we're negating air resistance, so in theory, there's nothing to slow the ball down. The length of time that the ball is traveling at this speed is determined by the vertical section of the problem. The vertical section starts with an initial velocity of 3 meters per second that we calculated previously. It has to end up negative 60 meters away from where it began on the roof of the car, and it has an acceleration due to gravity of negative 9.8 meters per second squared. Our goal here is to get a time so that we can figure out the horizontal displacement. The easiest way to calculate the time on our horizontal section is to create two separate problems for ourselves. So on the right we have a displacement versus time graph, and there's a red line showing how we're going to break it up. So part 1 is this section here, and we're going to use an initial velocity of 3 meters per second that we calculated previously, and a final velocity of 0 meters per second at that brief moment where the ball is not moving. So we can use the acceleration equation, change it around to put it in terms of time, use unit analysis, and do the math, and we get a time for this section of the graph of 0.3061 seconds. For the second half of the graph, we're going to use the displacement equation. The initial velocity here is 0, so we can negate that part of the equation, and we just end up with this edited equation, the square root of x divided by 1/2 a as the time. So again, we can set up our unit analysis. The square root of 3.0612 seconds squared is 1.7496 seconds for that half of the graph, and then we'd have to add the 0.3061 seconds from the previous half to get a total hang time in the air of 2.0557 seconds. So now we could fill some more stuff out in the chart we have. Time mainly. Time is the only thing that these two, the horizontal and vertical components, share. And now that we have a time, we can figure out the horizontal displacement to see how far the car has to travel to be hit by the ball. So we're also going to use our displacement equation here, and because our acceleration is 0, it's simply velocity, the initial velocity times the time, which ends up being 10.6818 meters, and we could fill that in our chart. We can figure out that the car needs to travel 29.3182 meters towards the cliff to be struck by the ball. The car also only has the total hang time of the ball to get there, or 2.0557 seconds. We can use the velocity equation, displacement over time or distance over time, to get a velocity of negative 14.2619 meters per second.